What's up guys, welcome back to my IB Computer Science video series. Today, we'll be going over topic B2, which covers most of the basic programming skills you'll need to know. This video is the Python version. If you're taking the course using Java, please check out the Java version of this video that I uploaded. This video will be structured slightly differently from the syllabus order, as I think IB's organization of the topic is quite ineffective. Instead, I'll be using my own order to teach the topic, while still covering the entire syllabus breadth. Here's the order in which I'll be teaching. This video is meant to be accessible to anyone at any coding level, so you can skip through the video if you're already familiar with some of these topics. I'll leave timestamps in the description and the pinned comment down below. But if you're a complete beginner to coding, I suggest that you watch the full video, starting with the complete basics from chapter 1. So what is coding? You can think of coding as writing ordered lists of instructions for a computer, like giving instructions to a chef. These ordered lists are called algorithms, just like how you would call the set of instructions that you give to a chef a recipe. And like chefs, computers execute code line by line starting from line 1, so it's important that we mind the order in which we write code. For our very first line of code, we can tell the computer to print something out. To do that, we write print and then specify what we want it to print inside of quotation marks. So this would print out hello world inside of the console. We can also define the sentence inside of a variable. So what we can do is we can write sentence equals to hello world. A variable is like a container that holds a piece of data. We call this statement declaring a variable, where we create a new variable and assign a value to it. When we want to access the data inside a variable, we can call this variable by using its identifier. And in this case, the identifier is sentence. So what we can do is write print sentence instead. So this print statement now calls the variable, meaning it prints out the value inside the variable, which is hello world. So if we just run this, we get the same result of hello world. We can also change the value of this variable. So we can just write sentence equals hello earth. And because this line of code then changes the sentence variable to hello earth, it'll print out hello earth inside the console this time. This statement, hello world, that we put around quotation marks is something we call a string. A string is any combination of characters put together. Strings are one of the fundamental data types in Python. Other data types include integers, characters, boolean, and float. A variable can also store data of any data type. So we can edit this boolean variable to equal 10.8. So now this boolean variable stores a float. Some data types let you perform additional operations on them. For example, we have an integer stored in the variable number. We can then add, subtract, multiply, or divide the value stored inside number with another value, so in this case 5. You can also use the percent symbol to find the remainder after division. We store all these results inside new variables listed over here. But if you want to update the variable itself, you can use the operation followed by an equal sign, like this. If you have strings, there are multiple different actions you can take. For example, if you have two different strings, you can concatenate them together, meaning stick them together. And you do that by using this add symbol. You can also find a string's length by using the len function, or convert all characters to upper or lowercase. You can also find a specific character's location in the string using .find, or print out specific parts of the string, which we call substrings. This line prints out the third character onwards of word 1. And this line prints out the second character onwards until and not including the fourth character. So now if we just run this program, we'll be able to see the results. You can also compare different values by using any of these. These are called conditional operators. The resulting output is a Boolean value stating whether the comparison is true or false. So here, we stored the result of number 1 is greater than number 2 in the variable result1. So if number 1 is greater than number 2, result 1 will store true, and if not, it'll store false. You can print this value as well, so of course this will print true. For characters, the comparison is based off the ASCII code that is assigned to. Strings run off the same principle, with the first letter being prioritized. So here, because car1 is not equal to car2, this will print false, and we can see that in action over here. The main use case for these are if statements. An if statement only executes the inside code if the condition is true. So here we have two variables, number 1 and number 2. And because they're equal, this condition is true, meaning that this inside code runs, which means that if we run the program right now, we'll see that this statement is printed. You can also attach an else statement like this. And inside here, this will only run if this code didn't run, or this code inside the if statement. So let's just say print like no, for example. And let's change the condition to say if number 1 is less than number 2. And because 5 isn't less than 5, this won't run, meaning that it'll default to the else statement. So if we run now, it'll print no. We can also attach elif statements, which is short for else if statements, and we can add another condition here. So let's just say something like this. Then if we run the program, we'll see that it still prints no because number 1 is indeed equal to number 2. Remember that the conditions are checked in order from top to bottom. With conditions, you can also optionally use one of these keywords. These resemble logic gates but for true and false instead of 1 and 0. If 2 conditions are placed like this with the AND keyword in between, then both conditions must be true for the entire statement to be true, which then allows this below code to run. And for example, if the OR keyword is used instead, then at least one of the conditions must be true for the below code to run. And if we want to use the NOT keyword like this, then the NOT keyword inverses the condition that it affects. So here, num3 is not less than num4, so this part will be false. But because we have a NOT, this will turn into true, meaning that this print statement will run. So let's just try it. And there we go. What if we wanted to repeat a block of code a set number of times? Instead of pasting the same block of code repeatedly, you can use loops. There's 2 kinds of loops. The first is a counted loop or for loop, which we'll explore right now. This loop repeats code while counting to a certain number. This for loop over here starts at 0 and then increments by 1 each time the loop is repeated. And when it hits 5, it stops repeating. The number it counts is stored in this variable I, which you can access anywhere within the loop. This for loop simply repeats this print statement 5 times. This for loop down here prints numbers sequentially from 0 to 4 by using the counter variable I. So remember, I starts at 0, and each time the loop is repeated, I increases by 1. So I would take the values 0, 1, 2, 3, and 4. The important thing to note is that when it hits 5, it doesn't execute the print statement over here. So let's try running this, and we can see it goes from 0, 1, 2, 3, 4, and it skips 5. We can also change the number that the loop repeats up to. So let's say we want to loop up to 10, or we can also change the starting number that the loop starts from. So if we want I to start from 2, we can do that too. And you can even set the increments of the I. So if we want I to increment by 2 each time, we can just write 2 over here as well. And so what happens here is I starts at 2, then each time it's repeated, I increases by 2, so it'll go 2, 4, 6, 8, and before it hits 10, it would stop executing the for loop. And we can see that in action over here. The other kind of loop is a conditional loop, or while loop. A conditional loop repeats the code while the condition holds true. For example, this while loop simply mimics a for loop, where a variable I is first set to 0, and each time the loop is repeated, the variable I is incremented by 1, and the loop repeats until I is not less than 5. But remember, this condition over here can be anything, like, for example, while a Boolean variable stays false. Thus, you need to be careful with conditional loops to make sure that indefinite loops don't happen. For example, if we were to remove this incrementing line and run the program, this program would go on forever. And you can see it just keeps printing I'm cool as time progresses. You can also write a loop inside of a loop. This is called nested loops. What happens is that let's say the outer for loop is on its first iteration, so I is equal to 0. Then this inner loop is repeated fully, so j goes from 0 to 4. Then I is incremented and j starts over from 0 and goes to 4 again. And I is incremented and then j repeats again, and so on. Make sure to set the loop variable as something other than I for the inner for loop, and the most common alternative is j. To recap so far, we've learned the fundamental topics in coding: print, variables, if statements, and loops. Let's now move on to a more complicated topic: data structures. Data structures provide different ways to store data other than variables. We'll start with lists. Previously, you could store one thing at a time per variable. Now, you can store a collection of different items into the same variable, and these special variables we call lists. To declare a list, we use the same syntax as we did for variables to set the list name, but then we use these square brackets to indicate that we're declaring a list instead of a regular variable. Then, we put the data in the list, separated by commas. This list that we call numbers is a collection of 7 integers. The elements can be any data type you want, and they can also be different from each other. So, for example, we can just write hello in here, and this is a string inside of a list of integers. And we can also just like make a character or make a float as well. Now let's say you want to change the values in this list. You can access individual elements by writing the list name followed by the index you want to access in square brackets. The first item always has an index of 0. Then you can use the same syntax you would use to change a variable's value. This code would change the first item in the list to 30. Or if you want the full list, you can just write the list name. So you can just write numbers. And if we want to print the list, we would write this. And there we go. There's a list printed. You can add or remove elements from lists too. To add elements, you can use the append, insert, or the extend operators. With append, you can add single elements at a time to the end of the list. So here, we would add the number 6 right behind the number 4. And the insert function allows you to specify which position you want something added to in a list. So here, we're telling the program to add the number 4 into position 0 of the list. So this 4 would go right in front of the number 5. And extend allows you to attach a list to an end of another list. So this numbers 2 list would just be appended right at the back of numbers. So it would go 2, 9, 4, 11, 34, 29, 76, 93. To remove elements, we can use either remove or pop. Remove is to remove the first instance of a specified value from the list, and pop is to remove a specific index from the list. So here, this line would remove this 2, and this line would remove this 5. Now let's look how to traverse a list. One way is to use the len operation and indexes. So here, we're using len numbers to get the amount of numbers inside of the list numbers, which this would just return 7. So it would be for I in range 7 and print numbers I. So we'll just be printing numbers 0, numbers 1, numbers 2, numbers 3, and so on, which goes to the entire list. But there's a nice trick to simplify this with for loops. This code means to repeat the loop as long as there's an element inside of the list. You can sequentially access the list's contents by using the loop variable I. So from here, you can do something like check each element of the list using an if statement, which allows you to search a list for something. But in here, we're just printing each element that is present in the list numbers. You can also nest lists inside of lists. Since you can put data of any data type in a list counts too. This results in higher dimension lists or 2D lists. You can technically nest as many lists as you want for higher dimension lists, but the syllabus only covers up to 2D lists. You can think of a 2D list as like a matrix of data, where the sublists represent different rows and the data takes up different columns. This code over here makes a 2D list with 3 rows, each row having 3 columns. You can also set each row to have a different number of elements, which makes an irregular 2D list. So something like this would be an irregular 2D list. To access different parts of a 2D list, you can do one of 3 things. If you just want the entire 2D list, then you can just simply type the list name, like here. If you want a specific row, you can put the row index like this, and this will return the specified row. So this would return the first row, which would be this part of the 2D matrix. And if you want a specific element in the specific row, you can put the row index first, and then the column index. So here, we're looking for row 1, column 2, which would be, row 2, column 3, which would be this row and this number right here, which would be 6. Then you can use the append or insert functions to add new elements into the list, or you can use remove or pop to remove elements like before. And now, if we run this program, we can see that it first prints the entire 2D list, and then it prints row 1, and then it prints the number 6 in row 1, column 2, and then it prints a modified list with 10 and 11, 12, 13 added as well. And or just 11 and 12 because we've removed 13 over here. To iterate through a 2D list, you need to use a nested for loop. Again, we can either use indexes or the special trick. If you want to use indexes, you need to obtain the number of rows and columns and use those for your bounds for the two loops. So here, we use the len function twice. And for the outer loop, we take the len of numbers, which is the entire 2D list. So we're basically just counting the amount of rows inside of the 2D list. And in the inner loop, we take the length of numbers I, which basically takes the length of each of the individual 1D lists, or the rows inside of the 2D list. And if you're using the trick, then you need to first retrieve each row in the list like this. And then for the second loop, you need to retrieve every element in the retrieved row. The loop variable row will take on the different 1D rows, so all of these 1D lists, and call will contain every element in each row, which covers the entire 2D list over the entire loop, going through each element in a row before moving on to the next row. So that's the basics of lists. Next, we'll look at two special forms of lists, stacks and queues. Both stacks and queues are new data structures that derive from lists. You can think of a stack data structure as a literal stack of plates. When you add a new plate or element, the plate is put at the bottom of the stack, and as you add more plates, it stacks up. When you want to retrieve a plate, you have to take it from the top of the stack. This is the principle of a stack. It operates using the last in, first out principle, or LIFO. So let's say we define a stack with a list that looks like this. Then you can kind of visualize the stack like something like this, where 8, the last element, is at the top of the stack, and 4 is at the bottom. So you can just think of 8 as the top plate and 4 as the bottom plate. Now there's 4 key operations that you can do on a stack. The first is push, which adds a new element onto the stack. So here we're kind of simulating the push function by using the .append function, and we're adding a 7 and then a 1. So you can just think of this as adding a 7 plate and then a 1 plate onto the stack. So now 1 will be the top plate and 4 will still be at the bottom. The next function is pop, which retrieves and removes the element at the top of the stack. So if we just declare a variable, pop1, and declare it to be stack.pop, it retrieves the element at the top of the stack and then also removes it from the stack. So pop1, because when we first call the pop function, it's going to take the very top of the stack, it's going to equal to 1, and then pop2 will be the next element after that, which will be 7. And so after this, the stack will return to its original form. The next one is peek, where it retrieves the elements at the top of the stack without removing it. So peek1 would just be equal to 8, but the stack would stay the same. And then the last is empty, which just checks if the stack is empty, which we've emulated using the if statement here. Next up is a queue. And this time you could think of a queue data structure as a literal queue of people. People enter the queue at the back of the queue, and people are removed from the queue from the front. And this is the first in, first out principle, or FIFO. So here we've defined a queue as another list, and you can think, or you can just visualize the queue as looking like this, with 4 in the front and 8 in the back. And again, there's 4 key operations, and the first is enqueue, which adds an element to the back of the queue. And again, we're using the .append function to simulate the enqueue function. And we've added 7 and 1 over here, which just means 7 and 1 are added to the back of the queue. So now the queue looks something like this. The next operation is dequeue, which retrieves and removes the element at the front of the queue. So here we're using .pop0 to remove the first element inside of this list, which simulates the dequeue function. And then if we do that, dequeue1 will become 4 because 4 was at the very front. And then dequeue2 will become 6 because 6 was next in line right behind 4. So now the queue would look something like this with 4 and 6 missing. And then again, we have the front function, which is just exactly the same as the peek function, but it just retrieves the element at the front of the queue. So here it would be 9. And then is empty is just the function to check if the queue is empty, which is the same as for the stack. And that's all you need to know about data structures. So to recap, we've got lists, 2D lists, stacks, and queues. The next concept to look at is called modularity. Modularity is when a big program is comprised of separate components that work together to make up the complete program. So instead of a big mosh pit of code squished together, code is usually structured so that different problems are solved by different chunks of code. For example, when making a calculator program, you can break the problem down into these 4 steps, taking user input, then do an operation, then get the result and show the user, and then allow for follow-up calculations. Each of these can then be considered separate problems until it's time to reassemble the final program. Modularity makes the code more reusable, easier to understand, and easier to trace an error when there's a problem with the code. Python implements modularity using functions. A function is a block of code defined by the user that can be called in the code whenever the user wants. To define a function in Python, use this syntax, def, and then the function name. This code defines a very basic function, where calling it simply runs this one line. Now that we've defined the function, we can call it with the function name, func, alongside a pair of brackets. Now, when we run the program, the contents of the function is ran once, which means that the function is printed out. So we've got the function over here. We can call the function multiple times, like this. Let's just do that. And if we run this, we get 3 lines of function. And we can also write something else on here, like function2. And if you run this, you can see function2 is repeated 3 times. But a function can be more than just a glorified container box for code. We can also define inputs for the function and make the function output a value as well. This is analogous to functions in maths. In maths, you define an input x, and then the function spits out an output f of x. To define inputs, you add parameters into this bracket next to the function name. These are your variables that you will input whenever you call the function. You can then use these inputs inside of the function. So here, I've told it to take any number x, then add 5 to it, and then print the result. So now, when I call the function, so I'll just do func, and then let's just say 5 for the input. And then now, when I run this program, it takes my defined value 5, and then adds 5 to it to print 10. Function calls can also become a value. To achieve this, you need to use the return keyword. The return keyword's job is to give function calls a value and close the function. This basically turns my function into a math function. When I call my function, you can basically think of it like the value f of 5, where f of x equals 2 times x plus 1. So now, if I store the call f of 5, or func5, into the variable result and print it, it will print the value f of 5, which here is 2 times 5 plus 1, which is 11. In a sense, the function call itself becomes a variable. So func5, because it equals 11, we're basically saying result is equal to 11, which basically sets the variable to 11, and we just print result, which is just printing 11. If a return keyword isn't reached, and the call reaches the end of the function, it simply returns nothing, which was the case for the 2 functions that we looked at earlier. The return keyword can also be used to end a function call early. So here, if we just write return and run it, nothing happens, because the return keyword returned nothing, so we just get a none over here. Let's make an example function, add, that adds 2 numbers together. We want the add function to take in 2 numbers, sum them together, and then return the sum. So first, we can define the function with 2 parameters, a and b. So let's just call the function add, and then we'll take 2 parameters, a and b, like this. And now, inside the function, we want to just add them together. So let's just say result equals a plus b. And then we want to just return the result. So let's just say return result. And there we go, that's it. And now, we can call the function with 2 inputs. So let's just say add 2, 3, for example. And if we just surround this with a print statement and run it, we should get 5. There we go. When you define variables inside functions, you'll notice that you can't actually access them outside of the function. This is because of a concept called scope. Python's scope restrictions are quite loose. If you define a variable inside of an if statement or a for loop, you can still access the variable outside of them. These are called global variables, but functions are the exception. As you can see, we have a variable, z, defined inside of the function. And if we try to print z and run this program, we get an error. And that's because z is a local variable, and z is local to the variable function, so we can't access it outside of it. There's a special trick that can be used with functions as well, called recursion. Recursion is the act of calling the function inside of the function itself. To understand recursion, we need to get a bit technical. Let's look back at the add function. When the function is called, it's put into something called a call stack. If the call terminates either by going through the entire function or when a return keyword is reached, the call is popped from the call stack. So here, the call is popped with the value 5. But in recursion, function calls can't finish without reaching the recursive call first, meaning additional calls are repeatedly put into the call stack while the original call stays stuck. So here, we've called the function recur with the value 4. So this is put into the call stack. Now, recur 4 looks something like this. If 4 is greater than 0, then print 4, and recur 4 minus 1. So this is like the self call. What we've done is just taken the definition of this function recur, and we just subbed in all the a's with 4s. So because we're self-calling recur with recur 4 minus 1, which is just 3, that gets put into the call stack, recur 3. And again, we've self-called recur here with 3 minus 1, which is just 2, and so on. This keeps happening until here. Now, the only way to exit this perpetual loop is for a function to not call itself, which it doesn't in the case of recur 0, because it doesn't fulfill the condition inside of this if statement. So this self-call never runs. Now, in this case, the recur 0 is then popped from the call stack because it finishes. And then the preceding calls can also finish their execution, which just pops calls out of the stack. Now, the total output of this recursive function would be 4, 3, 2, 1, because what we've done is, all the way back here, we've printed 4, and then we've printed 3, printed 2, printed 1, and then, of course, this print statement wouldn't run because this if statement. The important thing to note is that when a call is stuck because of recursion, the call cannot proceed. In this modified recursive function, where the self call is put before the print statement, the print cannot run until the self call is sorted. So again, if we call recur 4, the call stack fills up until recur 0. But now, after the call recur 0 can't call itself, so this if statement doesn't run, then recur 0 is popped, and only now can print 1 execute for recur 1, and so on for print 2, print 3, and print 4. And so the resulting output is therefore 1, 2, 3, and 4. Let's look at another example of recursion. This recursive function calculates the factorial of an input number. Let's say this function is called with a value of x equals 4. Now, since 4 is bigger than 1, it's not going to go into this if branch, it'll go to this else branch. And this else branch tells the function to return x multiplied by the factorial of x minus 1. So for factorial 4, the factorial 4 will then return 4 times factorial of x minus 1, which would be 3. Now let's turn our attention to this new call, factorial 3. Again, 3 is not less than or equal to 1, so it's going to go into this else branch again. And so factorial 3 will return 3 times factorial of 2. And we repeat this for factorial 2, because 2 is again not less than or equal to 1, so factorial 2 will equal to 2 times factorial 1. Now for factorial 1 is slightly different because 1 is actually less than or equal to 1. So factorial 1 will just simply return 1. So because factorial 1 returns 1, this factorial 1 for factorial 2 will also equal 1. So factorial 2 will just equal to 2 times 1, which is just 2. And now the factorial 2 call inside of factorial 3 will then become 2. And then factorial 3 will just become 3 times 2, which is 6. And now finally, we're back at the original call, factorial 4. Factorial 4 was 4 times factorial 3, but we just found out that factorial 3 was 6. So we can just replace this with 6. And so the original call will return 4 times 6, which would be 24. And we can just verify that by running this program. And there we go. We have 24 outputted in the console. For recursion to work, 2 things must be included in the recursive function. First is the presence of a base case. A base case is a part of the function that doesn't recursively call itself under specific conditions. In the factorial example, the base case was that if the parameter of the call is less than or equal to 1, then just return 1. Secondly, you must ensure that when you recursively call the function, the new parameter of the recursive call gets closer to the base case. In the factorial function, every time the function was called, the number got closer and closer to 1. So we started out at factorial 4, then we went to 3, then 2, then 1, which then just returns 1. These two ensure the recursion doesn't go on indefinitely. Let's go over another example of when recursion is used in programming. Hopefully, as we go through examples, you'll start to get the gist of when recursion can be used. In this function, we find the value of the nth term in the Fibonacci sequence. The fundamental definition of the Fibonacci sequence is that the first and second terms are 1, which we put as the base case. So if the input n is ever 1 or 2, meaning the first or second terms, then simply return 1. Then the third term is the first term plus the second term, the fourth term is the second term plus the third term, and so on. Let's trace what happens when the function is called with n equals 6. So to call Fibonacci 6, we'll just write fib6 is equal to fib4 plus fib5. Now the call fib4 is equal to fib2, so fib4 is equal to fib2 plus fib3. But we know that fib2 must be equal to 1, so we can just replace that with a 1. And now for fib3, that's just going to be equal to fib1 plus fib2. But because fib1 and fib2 are both 1, we can just write 1s for both of this, meaning that fib3 will equal to 2. So this will equal to 2, and fib4 will then equal to 3. And because fib4 equals to 3, we can replace this fib4 over here with 3 as well. Now for fib5 is equal to fib3 plus fib4. But we know that fib3 is equal to 2, and fib4 will be equal to 3. So fib5 will just be equal to 5. Sorry. Yep. And so fib5 will then just be equal to 5. And so fib6 will be equal to 3 plus 5 is equal to 8. And if we run the program, we should, yep, there it is. We got 8 in the console. When writing recursive algorithms, try doing these two things before writing any code. First, try identifying the base case. This is a fundamental definition for your problem. For example, in factorials, the fundamental definition is that 1 factorial is equal to 1. And in Fibonacci, the first and second terms are 1. Then, try writing the problem in terms of simpler versions of the problem itself. For example, 4 factorial can be written as 4 times 3 factorial, and 3 factorial can be written as 3 times 2 factorial, and so on. Each iteration is simplified by using the definition of the factorial, until we reach 1 factorial, whose fundamental definition is 1. In the Fibonacci sequence, the nth term can be written as the sum of the n-1th term and the n-2th term, and each of the n-1th term and the n-2th term can be written again with that same definition, until you get to the fundamental definitions that the first and the second term are 1. Recursion is great for solving certain problems with minimal code usage, but most times, recursion makes solving problems unnecessarily difficult and complex. It also uses up a lot of memory due to the call stack. If the exam questions don't specifically ask you to use recursion, don't be pressured to use it. And that's it for modularity and functions. Everything you've learned so far are used very frequently in coding. However, the next 2 chapters will cover slightly more abstract topics. Before we get into the new syntax in the chapter, let's talk about errors. In coding, there's 2 kinds of errors. Runtime errors are errors that happen while the code is running. This is different from compile time errors, which are errors in the actual code, like incorrectly writing syntax or using uninitialized variables, preventing the code from running at all. Examples of runtime errors include resource shortages like memory, invalid operations, invalid input, or trying to access array indexes that don't exist. Compile time errors are shown with red lines in most IDEs, so they can be solved before executing the code. Runtime errors are a problem because it causes the entire program to stop working, and they are usually random and unexpected. Fortunately, there's a way to deal with some runtime errors, with a new programming construct called try-except. The try-except block is a way to predict a certain runtime error, and provides a way for the program to continue if it encounters said runtime error. For example, this program has a divide function that divides 2 numbers and returns a result. This function works for any combination of 2 integers or floats, except for one scenario, when the second input is 0. If we try this and run the program, we get an error. We get this runtime error, 0 division error. So let's note that down. Now, since we know that there's a possibility that this exception could occur, we're going to predict it using a try-except block. So how this works is we're going to make a new line over here, and we're going to write try. And we're going to indent this line so that now return A divided by B is a part of the try. And now, below here, we're going to write except 0 division error. And now what this is if the code inside of the try block ever makes a 0 division error, it's going to stop running whatever it's running inside the try block, and it's going to run the code inside the except block now. So let's just print out like error, for example. And now, if we run this code, this is what we get. So of course we get the print error, but then we also get none, and that's just because this divide call returns nothing because this return statement is actually skipped because this return statement would otherwise make a runtime error. We can also add another part called finally, and here is code that runs no matter what, or no matter if an exception is caught or not. So here we can just write like the try except block has finished, something like this. And now if we run it, we get error, and then the try except block has finished because we print this, then we print this, and then we print the result of divide 10, 0, which of course none. I should add though that exception handlers aren't necessary in most cases, especially in an IB exam context. So when you're writing code for an exam, unless they specifically ask you to use exception handlers, you don't have to think about exception handlers much. Like in this example, an if statement would be a much more intuitive solution. But there's one specific situation where you absolutely must use exception handlers, file processing. In this chapter, we'll learn how to write to and read from files, and understand why exception handlers are very important here. In Python, you can access and manipulate files using these 5 commands. The first 2 are open and close, which both do exactly what they sound like. They open and close a text file. When you open a text file, you need to specify the file name alongside the mode that you're opening in, meaning are you opening to read, write, or append. Then this file is stored inside of a local variable, which we've just called file. And anytime we want to access the file, we do it through this local variable. Then, after we're done manipulating the file, we must close it with the .close function. And this just finalizes any changes we've made to the file. And now, if we want to manipulate the file, we must do it in between this open and this close function. Let's say you choose the write mode when opening the file. The write mode allows you to create a text file. If a text file with the same name already exists, then the file is overridden. Once you've opened the file in write mode, as we've done here, you could then use the write function to add text into the file using strings. So what we can do is write file.write, and then inside the brackets, we can write a string to add. So let's just write hello. And then what we're going to do is we're going to add this backslash and an n. And what this does is it just creates a new line inside of the text file. So now, that will just create a hello, and then it's going to make a new line. And then again, we can just write file.write, and here we can say, I'm an IBCS student, like that. And now, if we run this, it won't print anything to the console, but now you can see that there is a file written inside of our folder. And if we open it, we can see it prints out, hello, I'm an IBCS student. And if you want to add to an already existing file, you can use append mode when opening the file. So to do that, we just change this W into an A. And now if we run this, again, it won't print anything. But if we now go to our file, we can see that what we had before is already here. But here we have a new hello, and I'm an IBCS student. And of course, this hello is put onto the same line as I'm an IBCS student because we didn't actually make a new line over here. Now let's say you choose the read mode. In the read mode, you can only perform operations that read data from the file. So let's go into read mode by changing this to an R. And of course, because we are reading, these write functions are useless. So let's just delete them. Now to read all data from the file, use file.read. And this reads all the text inside of the file. And what we can do is we can then store this inside of a variable. So we can just call this read. And now what we can do is we can just print read, and if we do that, we get everything inside of the file that we've written so far. Another read function is read line, which reads a singular line from the text file. So if we just change this to read line and print, we just get the first line of the text file. And what we can do with read line is use a for loop to print the entire text file. So what we can do is just delete all this and say for line in file, and inside of here we can write print line, and if we do that, we get the entire file printed out for us. Alternatively, the read lines function reads every line and puts each line into a separate element in a list. So what we can do is we can do li is equal to file.readlines. And if we were to print li, we will get each of the lines inside of the text file into a separate element inside of the list. But sometimes when you use read mode or append mode, the file might not exist, causing Python to throw an error message when running the code. For example, if this was file2.txt, Python would throw a file not found error because the specified file isn't found. How do we solve this? Well, what we can do is we can just indent this one line, and we can write try. And then down here, we can write except file not found error. And inside of here, we can just write whatever we want. So we can just say print file not found. And now if you run it, because file2 doesn't exist, obviously it's going to stop at this line, and then it's going to go into this except block. So what we should get is this file not found. And there it is. We've now covered all the basics of Python that you need to know. Now it's time to bring all the concepts we've learned together for the final topic, algorithms. This is where we'll be looking at code made to solve actual problems, instead of just code for the sake of it. Firstly, let's understand how to analyze a given algorithm. We do this using trace tables. Trace tables are just a way to track how an algorithm runs by looking at how the internal variables change over time. Take this algorithm that takes in a list and increments one of two variables depending on whether the list element is odd or even. Let's make a trace table for this algorithm for this input list. In this algorithm, there's three variables. There's the loop variable I, there's also odd, and there's also even. Now, initially, I doesn't have a value, and odd and even start at 0. So we can just fill in the first row like this. First, I takes the value 5, because 5 is the first value of this input list, so we can just write 5 over here. Now, inside of this for loop, it states that if I modulus 2 is equal to 0, then increment even by 1. So in this case, if 5 modulus 2 is equal to 0, then increment even by 1. But 5 modulus 2 isn't equal to 0, it's equal to 1. So it goes into this else block over here. Now this else block says to increment odd by 1. So when I takes the value 5, it increments odd by 1, and even stays at 0. And that's the second row done. Now moving on to the third row, I takes the value 2, because 2 is the next input. Now, if 2 modulus 2 is equal to 0, then increment even by 1. And 2 modulus 2 is indeed equal to 0. So odd stays at 1, and even stays, or not stays, increments by 1. And now we can keep going for each subsequent element inside of the list. So 9, it would increment odd by 1, and 3 would increment odd by 1 again, and so on. We can do this for each element in the list to complete the trace table. By using truth tables, we can pinpoint where errors happen, analyze how variables change over time, and understand how an algorithm works. It's important that algorithms solve problems in the most efficient way possible. This means that algorithms use as little time and memory as possible. But how do we measure this? We can't measure exactly how many seconds an algorithm runs for, or exactly how many bytes of memory are used. Instead, we use something called time and space complexity. These tell us how much time or space is needed relative to the size of our input data. Let's look back at the algorithm we looked at. We need to consider how much memory and time this algorithm is using. Let's start with time. If the input list is size 8, it's like in here, this for loop loops 8 times. If the list was size 5, then the loop would loop 5 times. And if the list was size n, where n is any size, then this loop would loop n times. In this case, we say that the time taken as a function of n, so t of n, where n is just the input size, is equal to n, meaning input size and time taken has a linear relationship. Thus, we say that the algorithm has a time complexity of O n. But no matter how big the input list is, the algorithm only ever defines 3 variables, I, odd, and even. These variables then takes fixed portions of memory. Since these portions of memory are the only memory used, we say that the space complexity of the algorithm is constant, which we denote as O of 1, this meaning constant. When finding time and space complexity, it's also useful to draw their truth tables so you can visualize how many iterations it takes for different input sizes. These are some of the possible values for the big O notation. Each big O notation represents a different relationship between the input size, n, and the time taken, t of n, or the memory used, S of n. But one important note is that T of n and S of n aren't actually the time and space complexities. It's the big O notation that you need to write. So even if the relationship between input size and time taken was something like T of n is equal to 2n, maybe it's for an algorithm where it has 2 for loops in a row, then you still write, for the time complexity, you still write O of n as your final answer for the time complexity, because this is still a linear relationship. Even though there's a 2 here, this n is the only part that defines the relationship between the input size and the time taken. So never write T of n as your final answer, but you should write O of n instead. You just remember, for the complexities, the coefficient doesn't matter. All that matters is the relationship itself. Now let's go over all the algorithms you will need for this course. These can be categorized into search algorithms and sort algorithms. We'll cover search algorithms first. The linear search is one way to search a data structure like a list. This algorithm searches through an input list, which we denote as li, for a specific value, which we denote as input. To do this, the code starts at index 0 in the list and compares the item in the list to the search value. If there is no match, the code moves on to the next index and repeats this until the item is found, in which case it returns the index that it found the item in, which in this case is just the loop variable I. But if the entire list is exhausted without finding the item, it returns -1. We can see this algorithm in action when we run the program. We have a list, li, and we're searching for the value 11, which is in position 0, 1, 2, 3, 4, 5, 6 in the list. And now if you run it, sure enough, it prints 6. Key advantages of linear search include it's simple to implement and it works on an unsorted list. Its time complexity is O of n and its space complexity is O of 1, as the possible amount of iterations depends on the size of the list, and it only ever defines one variable, which is just the loop variable I. The other searching algorithm is binary search. Binary search only works on sorted lists. How it works is it finds the middle value, compares the target value to the middle value, and then rules out the half that must not contain the target. This process repeats for smaller sublists until the target value is narrowed down. For example, say we want to find the value 66 in this sorted list. We first retrieve the middle value, 31. Now, since 66 is bigger than 31, we can now rule out 31 and this entire left side of the list. Now, we can just focus on this smaller list over here. In this smaller list, the middle value is now 60. Since 66 is still bigger than 60, we can now rule out 60 and this side of the smaller list. And now, in this even smaller list, the middle value is 74. And now, since 66 is smaller than 74, we can just rule out 74 and this right side of the array. And there we go. Now we just have 66 remaining. Thus, we have found our target value in only 3 iterations, as opposed to 4, 8, 12, 13 iterations if we had used linear search. Here's a function that performs binary search on an input list li, searching for a specific input. We first define variables low and high to point to the list's first and last element. Then, we define the variable mid as the middle element by taking the mean of the low and high pointers. We use this double / to make sure that this value returns an integer instead of a float. Because if it was a float, then all of this code down here wouldn't work. Then we compare our target value to the list's middle value. And we update the low and high pointers accordingly, which essentially just narrows down our list. Here's a diagram for what's going on. You can see that initially the low, mid, and high pointers point to their list elements. Now the code low equals mid plus 1 essentially puts our pointer here. And what that does is it narrows down the scope of where we're looking inside of the list to just this little part only. That's defined by the elements between the low and the high pointers. And similarly, the code high equals mid minus 1 puts our high pointer here, which limits our scope to this part, which just rules out the entire right side of this entire list. And then after we move our mid pointer to here, right in between low and high, you can see that this is now our new sublist that we're looking at, just like we described when we first looked at binary search. And this keeps going until, like, we can put our high pointer here, or we can just put our low pointer here. And this process keeps going until the mid pointer points to the elements that we're actually searching for. So if the middle value is ever our target, we return the middle index as the index we searched for. But if not, then we just update the low and high pointers accordingly. We want this to loop while the array still has unexplored area, meaning when our low variable is less than or equal to our high variable. If this condition isn't true, that means the entire list has been exhausted without finding our target, meaning that the search was unsuccessful. So we just return a -1. This algorithm has a time complexity of O of log n and a space complexity of O of 1, as the variables we define always remain constant. So now, if we run this program by inputting this example list, and we're going to search for the number 11, which is in position 0, 1, 2, 3, 4, 5, 6, 7, this program should, it prints out 7. Now let's move on to sorting algorithms. We need to be able to sort an unsorted list. In coding, there's a lot of different ways to do this, but for this course, we'll be looking at bubble sort, selection sort, and for HL, quick sort. The first sorting algorithm is bubble sort. Bubble sort works by repeatedly swapping adjacent elements until the list is sorted. Let's say that we want to sort this unsorted list in ascending order. We start with these two elements at the front of the list. Since 13 is bigger than 8, we swap these two elements around. So what that looks like is like that. Now, we look at this new pair, 13 and 35. Since 35 is bigger than 13, we don't need to swap these two. We just leave it like so. Next, we look at 35 and 26. And since 35 is bigger than 26, we swap these two elements around as well. And now the list looks like this. And finally, we look at this pair, 35 and 19. And because 35 is bigger than 19, we swap these two around again. And now we've completed a pass through the list. And note that after this one pass, the biggest number, 35, was put onto the far right. We then start over at the beginning and repeat. So 8 isn't bigger than 13, so we don't swap these two. Now 13 isn't bigger than 26, so again, we don't swap these two. And 26 is bigger than 19, so we swap these two elements around. And that's another pass complete. Again, the biggest number that remained, 26, is put on the rightmost spot, one spot before 35. Now, since we know that the biggest number ends up at the end in order, we don't need to compare these two anymore. We know that these will automatically be sorted. So again, we've completed another pass, and we're going to do another pass again. So is 8 bigger than 13? No, so we don't swap. Is 13 bigger than 19? Nope, so we don't swap. And is 19 bigger than 26? Nope, we don't swap. And so because we haven't swapped anything in that iteration, we know that this list is now sorted in ascending order. And it is. It's sorted 8, 13, 19, 26, 35 in ascending order, meaning that we've completed the sort. This is the algorithm for a bubble sort in Python. The function takes in a single list, li, as an argument. We first define n as the length of the list. Now, we define the number of passes to the list as n minus 1, and loop until that. We then define a Boolean variable, swap. This will determine if during a pass to the list we have swapped at all, and we'll see why this is useful in a bit. Now, let's actually loop through the list and swap some elements. We want to loop through the list minus the elements we've already swapped. So we'll go through this for loop until n minus I minus 1. So in the first pass, I is equal to 0. So this loop would loop until n minus 0 minus 1, which is just n minus 1. Now in the second pass, I would be equal to 1. So this would loop until n minus 1 minus 1, or n minus 2. And this just ensures that all the biggest numbers that we've pushed to the right after every pass isn't considered inside the sorting algorithm. Now, since j starts from 0, we can access the first two elements of the list with lij and lij plus 1. So this would be li0 and this would be li0 plus 1, which is li1. We now compare these values, and if lij is bigger, we first set the swap variable to true, and then we swap the two elements with this line over here. This repeats for every adjacent element from left to right until the loop terminates. So in the second loop, j would equal to 1. So then we compare the elements li1 and li1 plus 1, which is li2. And this continues until, of course, we've completed a pass through the list. And if there are no swaps in the pass, we tell the loop to stop and finish the algorithm early. This is because in this case, we know that the sorting has finished. And then we just simply return the sorted list. Now, when we sort the example list from before, store it inside of a new list, sorted li, and then print it by running the program, we can see that the program outputs the correct sorted list. The time complexity of bubble sort is big O of n squared, meaning that in the worst case, for an input list of size n, a total of n squared iterations need to be performed. And space complexity stays at O of 1, as the defined variables are constant for any list of size n. A second method of sorting is selection sort. Selection sort isn't just mindless swapping between elements like bubble sort. Instead, it chooses beforehand the maximum or minimum value, then makes a swap. Let's understand this using a descending order example. In this example array, we see that 35 is the maximum value between all of these elements. And since the maximum number needs to be at the very left in descending order, we want to put 35 at this leftmost spot where 13 is. But right now 35 is in the middle and not the front. So what we do is we just swap these two elements around, like this. And that's one pass through the array. Now we find the next maximum between the remaining numbers. So between 8, 13, 26, and 19, we see that 26 is the maximum number. And so what we do is we take this 26 and we swap it into this next slot over here. And then we keep going until the array is fully sorted. So here, 19 would be the next maximum, so we swap these two like this. And now between these two, 13 is the maximum, and so we would swap like that. This is the algorithm for selection sort, also taking in a single list li. This time, the algorithm sorts in descending order. So like before, we define n to be the length of the list, and then define the number of passes through the list as n minus 1 with this for loop. Now for each pass, we define two variables, max num and max index. Now we loop through the list again from I to n. The reason we do I to n is because after each pass, we want to ignore the elements on the left side of the list that's already been sorted. Then we find the maximum value from the unsorted elements and store its index into max index. So now, after getting the maximum value and getting the index of the maximum value, we just need to swap the leftmost element with this maximum value with this code over here, completing a pass. Now this is repeated until the full list is sorted, and we finish by just returning the sorted array. Now again, if we input this example array into the function, and then store it into sorted li, and then print it, so we just run the code, we get the list in descending order. Now if we wanted to do ascending order, we would need to change the code so that it finds the minimum value each pass and swaps it with the leftmost element, while here we're finding the maximums each time. The time complexity of selection sort is also O of n squared, and the time complexity of selection sort is also O of n squared, and the reason is similar to the bubble sort. It's because of this nested for loop over here. And the space complexity stays at O of 1. So when would you use bubble sort versus selection sort? Well, to be honest, both are actually really inefficient in the world of sorting algorithms. Their time complexities of O of n squared make them terrible at sorting large datasets. But they do have some specific advantages over each other. Bubble sort is good at sorting almost sorted datasets. It can know preemptively when a database is sorted, thanks to the swap Boolean variable. Selection sort is good because of the reduced number of swaps in a very unsorted dataset. Python might make the swap look easy with this one line of code, but in reality, in the behind the scenes, to execute the swap, a temporary variable is first created, then one of the variables writes to the temporary variable, then the other variable overwrites the first variable, and then the second variable takes the value of the temporary variable. So in cases where writing to new variables is computationally expensive, selection sort can actually beat bubble sort in efficiency. Let's now explore one more sorting algorithm, quicksort. To start, we pick a pivot. The pivot can be any number. Then, put every number less than the pivot into another list, and vice versa for every number greater than the pivot. And repeat this process until every sublist consists of one element. Then, assemble these sublists back together in the order the less than sublist, and then the pivot, and then the greater than sublist. So consider this given list. We'll use quicksort to sort this list in ascending order. First, let's pick a pivot. Since it can be anything, let's just pick the first element to be our pivot. Now, let's put every number less than the pivot to the left, and vice versa for the right. So we'll start from the left and go in order until the right. So 7, 16, they're both less than 35, so these will just stay on the left side. Now 79 and 82 are both bigger than 35, so we'll move them to the right side. 11 is less than 35, so we'll just put it here. 43 is bigger than 35, and so is 61, and so is 98, so these will stay here. 22 is less than 35, so we'll put it over here. And now all of these numbers are bigger than 35, so we'll just put them in like so, something like this. And now we repeat this for these smaller sublists that have been created. And eventually what we get is a sorted list. It might sound complicated on paper, but in practice, this beats out both bubble sort and selection sort in time complexity, with an average time complexity of O of n log n. However, implementing quicksort is arguably the most complicated. So here's the code for it, and as you can see, it has a recursive term down here. So let's analyze this code line by line first. Here, we have our base case to prevent infinite recursion. It ensures that recursion stops once lists of sizes 1 and below are reached. Now, we define our pivot to be the list's first element, and define two empty lists, left and right. These mimic the spaces to the left and right of the pivot, like we showed earlier. Now, we implement the logic that places the list values excluding the pivot into the correct list, left or right. So here, we start from the first element of the list with this 1 colon notation, and inside of here, we compare each value of the list to the pivot. And here, if it's less than the pivot, then we put this x into the left list, and if not, meaning that x is greater than the pivot, then we put it into the right list. And finally, we have our recursive statement. We write it like this to make sure that when assembling our final sorted list, we have our sorted left list on the left, then our pivot, then our sorted right list, which overall, it makes a sorted list. Here's a diagram tracing the recursive calls of quicksort. So here's our initial unsorted list. So firstly, we choose 35 as the pivot, as it's the first element of this entire list. So after rearranging into the left and right sublists, the sublist then looks something like this. So this light blue color will represent the numbers selected as the pivots for that iteration. So we see that the numbers less than 35, 7, 16, 11, and 22, are put into this list called left. And these numbers that are all greater than 35 are then put into this separate list called right. Now we need to repeat this process for both this left and right sublists. That's what the recursive call does. So this is the next iteration. And this darker blue color just represents how much time has passed since the element was the pivot. So 35 is an old pivot, you could say. So now we've chosen 7 and 79 as the pivots, because 7 and 79 were the first elements of each of their lists. So if 7 was the pivot, all of these numbers are already greater than 7, so these just go to form a new list, a new right list for this little sublist over here, with 7 being the pivot. And on this side, the left and right sublists are made again. So 43, 61, and 54, they're all less than 79. So this makes up the left list for this part of the list. And 82 and 98 then make up the right list for this sublist over here. And then we do the process again. So this would be the next recursive call. And here we would choose 16, 43, and 82 as our new pivots. So again, 7, 35, and 79 are now old pivots. And now we're just going to look at the new pivots. 16 is the new pivot here. And 11 is less than 16. So it gets moved on to this left list over here. And 22 stays in position in this right list. And what you notice here is 11 and 22 both are now inside of lists of size 1, which means that this part will not execute anymore. Like, it won't recursively call anymore, because remember, our base case says that if the list size is size 1, then don't continue the recursive calls. And that's perfectly fine, because we see that this part is now sorted. And now on this right side, we see that 82 is the pivot on this side, and 98 just goes to this right side. And because 98 is in a list of size 1, this part is then sorted. We don't need to do anything else. And
we can even see that 79, 82, and 98 are now in their correct orders. Now on this side, this last remaining sublist, you can say, 43 was a pivot, but then 61 and 54 are both greater than 43, so this right list over here contains 2 indexes. So we're going to need to do one more iteration. And this next iteration looks something like this. 61 is then chosen as the pivot, and 54 is then moved to the left list. So now 54 is put into a list of size 1. So this part we can consider sorted. And now if we look at the bigger picture, we can see that the entire list is now sorted. 7, 11, 16, 22, 35, 43, 54, 61, 79, 82, and 98. So eventually, after dissecting and dissecting and dissecting all of these different sublists into even smaller and smaller sublists, we can see that eventually quicksort does its job. And surprisingly, in only 5 iterations as well. And now that we've explored how this code kind of works, let's try run it now. And we can see that this list has been successfully sorted over here into the correct ascending order. And that's all you'll need for basic programming skills. But there's a lot more programming in the course, especially for HL. So be sure to check out my future videos on B3 and B4. But for now, thank you for watching.